Welcome to the second chapter. In this chapter, we're going to be discussing your atoms, your elements, compounds, and all that. So we're going to start getting ready to discuss the real chemistry. We are going to start by just giving you some definitions of matter. For example, the definition of an element, which is what you're going to find in your periodic table, roughly 118 elements. An element is the simplest type of substance with a unique physical and chemical properties. An element consists of only one type of atom, and we discussed what an atom was. It cannot be broken into simpler substance by physical or chemical means. We also have the definition of a molecule. A molecule is a structure that consists of two or more atoms. So for example, this will be a molecule because there's two nitrogens in there. Or if we say this will be a molecule because there are more than one phosphorus in there. And these are chemically bound together. There is a bond between them, and it's a chemical bond. So it behaves as an independent unit. So they like to be together. We also have a compound, which is a substance composed of two or more elements that are chemically combined. So for example, H2. They don't necessarily have to be the same. Actually, they should be different. Mixture is when you have two or more elements, elements or compounds that are physically intermingled. So for example, if you have water and salt, this will be a mixture because you have these two different compounds in which creates one solution. So I'm going to be repeating these definitions a lot just so you can get familiar with them and be able to, you know, familiarize yourself with it. So as you may or may not know, everything is made out of these little particles that we call atoms, right? And these atoms, there's different types. So remember the atoms and elements are going to be two terms that we use quite a bit and we interchange them a lot. So for example, hydrogens, oxygens, carbons, everything, even the biggest building is made out of these elements, out of these atoms that you guys see. An element is what you guys, like as I mentioned earlier, have in your periodic table. There are about 118 elements. These elements are composed of only one type of atom. This is why we interchange those two terms. For example, copper is an element, carbon is an element, it's made out of only carbon, and so on. Notice here, we see that these substances are only made out of copper atoms, carbon atoms, or in this case, those are helium atoms. Now, a molecule is going to be when you have atoms that are joined together and they're going to be through a chemical bond. So it's two of the exact, so for example, we have oxygen O2 because you have more than one element, it becomes a molecule. So just by itself, like for example, gold, this would be an atomic element. But oxygen will consider a molecule because now you have atoms chemically joined together. Moving on. So here we have 7, at least for now, that you're going to have to memorize. 7 molecules, and those are going to be nitrogen, hydrogen, fluorine, oxygen, iodine, chlorine, and bromine. There's this saying that helps you memorize. Have no fear, for of ice cold beer. So here the H stands for your hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. And those are the ones that prefer to exist with each other as a molecule in pairs, as twins. Okay, the other ones are considered atomic elements. And as you know, we have roughly 118. This is 114, but I think now we're up to 118. These are the elements that are going to be in your periodic table. This is an atomic element because it likes to just exist by itself. Carbon is an atomic element, so it has the symbol. Remember, you have to memorize these elements. If it has two letters, the first letter is capital, the second one is lowercase. If it only has one letter, it's considered a capital letter. Elements cannot physically be separated, so you can't separate the gold, the atoms of gold. You cannot do it. It's only going, you cannot do it physically. You're going to have to do some extreme measurements if you were able to separate that, but that doesn't happen. Now they are, when obviously we have this idea of that elements and all of that stuff, we started leading and coming out with theories that kind of let us allow us to get some type of explanation on how these elements behave. So we started by developing 3 laws. These laws are the law of conservation of mass, the law of defined proportions, and the law of multiple proportions. So I'm going to give you a rough summary of all 3 so you can become familiar with them. The first one, the law of conservation of mass, states the matter is not created nor destroyed chemically or physically. The law of defined proportions states that 2 samples of the same compound will always contain the same elemental composition. You don't need to worry about the dates. And the law of multiple proportions, if the same element form multiple compounds, a ratio can be found between their respective elemental composition. So we're gonna dig a little bit into it so you guys know what I'm referring to. So the law of conservation of mass was developed by Antoine Lavoisier. I'm sure I'm mispronouncing her name. Pretty much this law states that a chemical reaction, you are not going to create nor destroy matter. And this is what kind of like the same idea for energy. So basically, if you start with a certain amount, you're going to end up with a certain amount. So here we have an example where we know that sodium and chlorine form sodium chloride. So here we're having 7.5 grams of sodium and 11.9 grams of chlorine, which that means that the product must be 19.6 because we need to make sure that the amount of the reactants equals the amount of products, because we cannot destroy nor can we create matter. Here's another example where we have calcium oxide. We have 56 grams and 56.08, and we have carbon dioxide. When these 2 compounds combine, they are going to form calcium carbonate. The amount, if you don't know it, all you need to do is make sure that you add up the 2 reactants, and that should tell you how much product you're going to have. Now, in the lab, you usually are not going to get that 100% yield. The reason for that is because we have many errors that happen. We are learning, so you're gonna spill something or whatever the case may be. Moving on to the second law, and this is by Joseph Proust, the law of defined proportions. A given compound always contains elements in certain proportions by mass. So for example, and I put a video in case you guys are wanna, kind of just go over a little bit more. For example, if we're looking at water, the ratio is going to be 16 to 2, or we simplify it, 8 to 2. Where does the 16 come? The 16 is going to come from the mass. The mass of oxygen is 16, and the mass of hydrogen is 1. But since water is H2O, so this is going to be 16, 1 times 2 is 2, so it's going to be 16 to 2. Or if we reduce it, the mass ratio is going to be 8 to 1. So every time you have a ratio of 8 oxygen to, or 16 oxygen to 2 hydrogen, you're always going to have water. And it doesn't matter where you take those elements. So for example, copper carbonate. Copper carbonate is going to be composed of carbon, hydrogen, oxygen, and copper. It doesn't matter where they individually come from. What matters is when they get together, what kind of mass ratio they're going to have. And that's pretty much what it's saying, what the law is saying. It doesn't matter where individual those elements comes. What matters is when they come together, what is that ratio? It is important that you know the name of the law and who discovered the law. The third law was discovered by John Dalton, and this is the law of multiple proportions. This law says that when two elements, and we're gonna call them A and B, form different compounds, the masses of element B combined with the mass of element A can be expressed as a ratio of small whole numbers. So we always want to represent it in small numbers. For example, what they're saying is A and B can exist in different ratios. This is a different compound than this is. So even though A and B is there, but just because, so we'll give you an example, H2O versus H3O. They both have hydrogen, they both have oxygen, but because the ratio to hydrogen to oxygen is different, they are completely different compounds. This is water and this is acid. Also, what that law is saying is that we always want to represent it in the lowest rate, in the lowest possibly ratio. So for example, here you can reduce it, right? Because it's 2 to 1, you can reduce it. But if I was to give you this, you wouldn't show it, you wouldn't give it to me like that. You will reduce it to HO because you divide both by 2, you can reduce it. So that's what pretty much that law is saying. Another example, notice that here we have carbon dioxide and carbon monoxide. They both have carbon and they both have oxygen, but those ratios are different. One, carbon dioxide, which is, naturally, carbon monoxide, which could potentially kill you. Both gases, one is more harmful than the other. So here's another video just to kind of give you more information about that law. Finally, what took place after all those 3 laws, Dalton came out with a theory. So first came those 3 laws, then Dalton developed a what's called the atomic theory, which is pretty much a summary of all these 3 laws. Make sure you become familiar with this. Dalton's theory has a few points. Number 1, or a few postulates. All matter consists of atoms, tiny indivisible particles of elements that cannot be created nor destroyed. So what they're saying right now, at this point, we believe that the atoms is the smallest particle that we cannot destroy it. Atoms of one element cannot be converted into atoms of another element. Atoms of elements are identical in mass and other properties are different from the atoms of any other element. Compounds result from a chemical combination of specific ratios of atoms in different elements. So basically what we just went over, they're just summarizing. Okay, so after, so in Dalton's theory, so pretty much the mass of conservation can be understood on, if you look at postulate 1, 2, and 3. So the 1 says atoms cannot be created nor destroyed, which is pretty much the conservation of mass. Postulate 2, or converted into any other type of atoms. 3, since every atom has a fixed mass. So during a chemical reaction, pretty much summarizes that we cannot create nor can we destroy matters. Also, it gives you, so the defined composition is explained by postulate 4 and postulate 3. You don't need to necessarily memorize this, but it just kind of gives you an idea on how It gives you an idea on how those different laws is being explained through his theory. The last one is multiple proportions, which is pretty much explained by partial 3 and 1. Okay, so after all of this, there were some answer questions, and I put this. After this theory that was developed, there were some answer questions such as, what does an atom look like? Why is it that sodium and phosphorus, they, even though they're different elements, they have similar properties? Why is it that some compounds are able to combine, but others are not? So these questions were left unanswered. So since they were left unanswered, this brings us to kind of study, it's gonna bring us to kind of look at the atom more in detail. So what does the atom look like? So the atom, it's not the smallest part that, like we believed in Dalton's theory. The atom actually is composed of 3 subatomic particles. So it's not like the, you know, how we were saying that is indivisible, we can't break it apart. We actually can. Into 3 simple substances, which are your proton, your electron, and your neutron. The proton carries a positive charge and is inside the nucleus. The neutron has no charge and is also inside the nucleus. Outside the nucleus, there's this clouds, we're gonna call those clouds. And that's where you're going to find the electrons that are going to have a negative charge. Now, protons and neutrons are in the nucleus. Below, if you look at your periodic table, you're going to see helium, and you're going to see, I believe the mass of helium is 4. You're gonna have a 4, so it's gonna be helium, and you're gonna have 4.00, and then it's gonna have a number of 2. That 2 is the atomic number. The atomic number equals the number of protons. So if I say I have 19 protons, what is the symbol? Well, you're gonna look that 19, it's gonna be potassium. Protons equals the number of neutrons. Protons plus neutrons equals the atomic number. So this 4 represents the atomic number. So since it has 2 protons, how do I know it has 2 protons? Because the atomic number is 2. And we know that the atomic mass is 4. So that means this element must have 2 neutrons. Okay, so make sure you try to understand that. If you need me to give more examples, let me know. Different elements equals different number of protons. So no element has the same number of protons because it has a unique atomic number. So if I ask you, what is I have 36 protons. What element am I talking about? You're gonna say krypton because krypton has 36 protons. How do I know? Because the atomic number is 36. So there is a video that kind of is going to walk you through the history of the atom, and we are going to start going over that. I'm going to need you to know the person who discovered a particle and the experiment that they use. You don't need to know the dates. We are going to start with J.J. Thomson. He is a scientist who conducted an experiment called cathode ray, which is a tube that pretty much, it's a tube that he did some experiments, and he used magnetic field and to pretty much discover the electron. So this tube that he did, he was putting cathode rays that were traveling from the negative part to the positive part that he called the anode. We don't need to know the details of the experiment itself, but what you do need to know is that this experiment, the cathode experiment, he was able to conclude that an electron had a negative charge, and that pretty much he cannot discover the magnitude of the charge, because you don't need to know the magnitude of the charge, but he was able to discover that it was charged with a negative particle. So J.J. Thomson was able to discover the electron, and it was able to discover that it had a negative charge. Now, the mass of the electron was later discovered through another physicist. His name is Robert Millikan, and he developed an oil drop experiment. And he was able to, through this experiment, he was able to figure out the mass of the electron, along with the mass of the electron. So the math, you don't have to know. So this is the equation that we use. And through this equation, we were able to determine the mass of the electron, which is 9.09 times 10 to the negative 28 grams, or 9.109 times 10 to the negative 31 kilograms. No need to memorize the number. You just need to memorize that Millikan was able to do an oil drop experiment, which allows us to determine the mass of the electron. Later on, there was another scientist who had a gold foil experiment. His name is Ernest Rutherford. This experiment allowed him to discover the nucleus. Okay, he discovered the nucleus, and so here's the kind of pictures of the experiment itself, which you don't need to necessarily know how it works. But what you do need to know is that this experiment allowed him to discover the nucleus. So to this experiment, pretty much he realized that after doing some research, he realized that there was something in the nucleus. So he had already discovered a nucleus, but it gave him some odd numbers. So he realized when he was, so here it is. So here's a nucleus, and he was shooting it, this gold foil experiment, he was shooting it with alpha particles. And what he realized that these alpha particles were not going always straight. Some of them were kind of deviating to a denser region. And the reason why they're deviating was because there was something else in there. And that something else had a particle. And what that was the proton. So Rutherford was able to discover the nucleus along with the protons. So this idea, he was able to, the conclusion from his experiment was that most atoms mass, so most of the mass of the atom comes from the positive particles that are in the nucleus. So basically the heaviest part of the atoms is in the nucleus. Most of the volume of the atom is an empty space. So that's when we knew that there was this clouds, and it made the atom bigger, but there was no much mass. But in this empty space, there were negative charged electrons. So that's where we find out, the electrons and the protons are not together. The electrons are in this outer space. And then he found out that inside the nucleus, there are positive charged particles, which are called the protons within the nucleus. So that was what we knew so far. So we know the nucleus, we know where the electron is located, we know the mass of the electron, so on. After him, there was two other scientists. One of the students, or rather four, discovered the neutron. So he kind of piggybacked on Rutherford's work and demonstrated that there was a neutron in the nucleus. Okay, so this is similar to the proton. However, the neutron has no charge. Okay, but it has a mass. So the denser part of the atom is in the nucleus. The nucleus has the protons and your neutrons. They have mass. The proton has a positive charge. The neutron does not have a charge, and the electron has a negative charge. Okay, so these are the three parts of an atom. Notice that the mass of each of these particles are here in kilograms. However, we're not going to be using kilograms. We're going to be using AMU. Notice that when we do that, we're going to realize that the mass of the electron, so basically when we convert the atomic mass unit, which is AMU, is going to be equals that many grams. So when we convert the mass of the electron to AMU, it comes out to almost zero. So the mass of a proton is going to be 1 AMU, the mass of a neutron, 1 AMU, and the mass of the electron, 0 AMU. That's why the denser part of the atom is in the center. The charge of the proton is +1. Charge of the neutron, 0. The charge of the electron is going to be -1. And you want to make sure that you know the location. So I'll give you a minute for you to try to answer this question. The answer for the first one is true. The answer for the second one is false. Remember that we didn't discover that the atom had subatomic particles until after Dalton's theory. Third one is D. Next one. The answer is C, because we found out that the atoms are composed of protons, neutrons, and electrons after the atomic theory, Dalton's theory. So this is not a part of Dalton's theory. The last one is Thomson discovered the electron, so it's false. This is a summary just to give you an idea. We're gonna represent number of protons with the letter Z, the mass number with the letter A. If you remember, the mass is gonna be protons plus neutrons. The charge is going to be protons minus electrons, and that's very important. Protons minus electrons. So if I tell you I have calcium and it has, well, you know that how many protons it has, because if you look at the atomic number, it's 20. If I tell you calcium has 18 electrons, what is the charge? Well, 20 minus 18 equals +2. So we're gonna represent it like that. Here is how we symbolize. This is the chemical symbol, which is gonna be one letter or two letters. The mass number, which is the atomic number, plus the neutrons. Here we have oxygen, number 8. That's how many protons, right? Or the atomic number. O is the symbol, capital letter. Oxygen is the name. 16 is the atomic mass, which is that number of protons plus the number of neutrons. Here's your periodic table that you should have one handy every exam. Notice here we have helium, He, carbon, capital C, nitrogen, lowercase n. We're gonna stop here and then we're gonna start seeing, I'm gonna leave you with this. Notice that this is the different elements. Be careful because if it's 2 letters, the second one must be lowercase. If you don't do this, this is carbon monoxide, where this is cobalt. So when it's 2 letters, make sure the first one is going to be capital and the second one lowercase. When we say we have a charge, the charge is gonna be as a superscript. This indicates how many electrons. So if you have a positive charge, that means you lost electrons. Why? Because the electrons carry a negative charge, right? When you have a negative charge, that means you're adding an electron. So this indicates that it lost 2 electrons. This indicates that it gained 1 electron. This indicates that it gains 2 electrons. It gains 2 electrons. Now, sometimes you're gonna see it represented here. And what this is saying is the atomic number is not gonna change. The atomic number will always be the same, because remember, if we start changing atomic numbers, now we start changing the element. So you will always be the same atomic number. So that's not gonna change. But what does it mean, the number at the top? That means that the mass is different. And remember, mass, so U is 92, right? 92. So this is never gonna change. But the mass is the number of protons plus the number of neutrons. So the protons for both of them is 92. But what changes now is the neutrons. And these are what called isotopes. And that's how we're gonna start our next name, isotope. Same number of protons, but different number of neutrons. Please let me know if you have any questions. Let's continue our discussion, and we're gonna pick up where we left off, discussing isotopes. Isotopes are going to be those elements that have the same number of protons. However, they are going to have different number of neutrons. For example, if we look at atomic number 10, that's going to stand for neon. So the atomic number is never gonna change. It's always gonna have 10 because protons never change. But you can have neon 10, neon 11, and neon 12. What that's referring is to the mass. So the number of neutrons are changing. When you look at the periodic table, you're going to see a atomic mass. That mass, you're gonna see that it has decimals. The reason for that is because what you are presented in the periodic table is going to be the average or the abundance of all the isotope, the mass of all the isotopes. And we are actually towards the end of this chapter, we're actually going to be doing calculations when it comes to that. So you can be able to calculate it. We actually use mass spectroscopy to actually allow us to determine the abundance, the percent. For example, you have carbon 13, carbon 14. Most elements have isotopes. So we want to know what is their abundance, right? How much of each there is in the universe. The way we're going to see that we represent isotopes is going to be different ways. For example, here, notice that we have neon 21, 20, 21, and 22. So this is the number of protons because this is the atomic number. So if I ask you how many neutrons, well, you're going to do 22 minus 10. This one has 12 neutrons. The other one, 21 minus 10, has 11 neutrons. And the 20 minus 10 has 10 neutrons. So these are the 3 different isotopes that we're going to be discussing. Sometimes we also represent it by just giving you the symbol. Why? Because if you know the symbol and if you look on the periodic table, you automatically are going to know that it has 10 protons because the atomic number is 10. and that never changes, okay? Notice here we have examples as the protons never change. However, the number of neutrons change, which means that the mass is different because the mass is the protons plus the neutrons. This gives you the abundance. Notice that the abundance is always gonna add up to 100%. I'm gonna give you a chance for you to go over and see if you can try to answer those questions by yourself. Here are the answers.
Yes.
Excuse my voice. Okay, now we are going to introduce another topic, and that is going to be ions. Ions, the word ions means it carries a charge. Now that charge is going to be positive or is going to be negative, okay? Now, if it's positive, that means that it's cation. The positive means that it lost electrons. When the element is negative charge, we are referring as anions. And what that means is that element gain electrons, okay? And we are going to be able to do some of those calculations. Diving deeper into the periodic table, the father of the periodic table is known as Dmitri Mendeleev. He started discovering the elements, started organizing them in a table. What he did is he put elements in rows and he put them in increasing of atomic weight. And he put elements in columns depending on the way they reacted. However, this gave us some problems. What we started realizing is that we didn't have all the atoms, so that he left blank spaces. These were undiscovered elements. And then there were some, he broke the pattern. There were some increasing atomic weight. So it wasn't that pattern where like, like the heavier becomes after. So there were some problems with that. So this is how the old periodic table looks. His periodic table contained gaps, which kind of allow him to kind of predict, saying there's something else out there, which now we know there was. This is the more modern periodic table, where elements are actually arranged in increasing of atomic number, not atomic weight. So when you go in the rows, they are going to increase on atomic number, not atomic weight. When you put them in a column, everything with the same color, they have similar properties. They have similar properties. Mendeleev had the right idea, but we made it a little bit different to kind of make sure that we cover all the things that he left unanswered. So the periodic table, we have 7 rows. Those are called periods. They are in order of atomic number, not atomic weight. We have 18 vertical columns, which are gonna call families. Sometimes they call them families, groups. We are going to be able to organize the periodic table in different ways. The first way of characterizing the periodic table is by dividing the periodic table into 3 major groups: the metals, the non-metals, and the metalloids. So everything you see in this tan color are metals. So the periodic table is mostly metals. Everything you see in this green color is your non-metals. So you have, I believe, 18 or 19 non-metals. And this in purple is the metalloid. So that's the first way of dividing the periodic table into three major groups. The metals, which are good conductors of energy. The reason for that is because metals like to get oxidized, meaning they like to get rid of electrons. So meaning metals are always going to carry a positive charge, meaning they're going to be cations, right? Because they like to get rid of electrons. They are shiny, they are solid at room temperature. They like to lose electrons, they like to get rid of electrons in a reaction, so they like to become cations. Nonmetals are poor conductors, they're brittle. Sometimes you can find them as a solid, as a liquid, or as a gas at room temperature. They become anions because they like to gain electrons in a reaction. They like to gain electrons. So that means they are going to carry a negative charge. Metalloids are semiconductors. They're kind of in between. They behave like metals. They behave like non-metals sometimes. So metals, metalloids, and non-metals. So I'm gonna give you just a little bit more for you to read, kind of just to become familiar with it. So those are often shiny. Those are your metals. Then you have your non-metals, which you have your helium, hydrogen, helium. Even though hydrogen, remember hydrogen is in group 1, but it's a non-metal. Helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon, rhodium. So those are just example of your 11 gases. These are non-metals. These are gases. You don't have to memorize this. And you have 5 that are solid at room temperature and 1 that is liquid at room temperature. Not necessary to memorize it, just good to become familiar with it. Non-metals, as I mentioned, they are poor conductors. They like to gain electrons, so they are going to be anions. Metalloids are going to be in between. They are going to have properties of metals and properties of non-metals. They are considered semiconductors. Another way of dividing the periodic table is into 2 main groups, and that will be your main group and your transition metals. The main group is going to be those elements whose properties we can predict. So they're predictable. The transition metals are the ones that can carry more than one charge, so they're less predictable. As you can see here, the ones, we're not gonna be concerned about the ones at the bottom, but we are gonna be concerned with the blue and the yellow. The blue represents your main group. Notice how they are renamed as the main group being 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Your B group becomes 3B and all the way through, right? So this whole part yellow is your transition metals. So they are metals, they're just transition metals. So it makes it a little bit more easier. So this is the periodic table that we're gonna be focusing on. Your main group is the in yellow and your transition elements are the one in blue. Now, within the main group, we are going to have some names. So this part is still the main group, the one that I'm circling in red. Still the main group. And with here, you see that the first group is actually called alkali metals. The second group is called alkaline earth metals. Group AA is called noble gases, and 7A is called the halogens. Sometimes this is called the oxygen family. Okay. Now the main group, oops, sorry. The main groups are going to tend to lose electrons. And they are going to become a cation. And the reason for doing that is because they're gonna wanna become like, they're gonna either gain or they're gonna lose in order to become like the noble gas near it. And the non-metals, let me explain this better. Let me go back to this periodic table. These are the main groups. These ones are going to lose one electron in order to become like the noble gas, except for hydrogen. Group 2 are going to lose 2 electrons in order to become like the noble gas. 7A is going to gain 1 electron in order to become like the nearest noble gas. 6, like oxygen, they're going to gain 2 electrons. Nitrogen is going to gain 3 electrons. Boron and carbon are a different story. So in general, alkali metals, which is your group 1A, are going to be able to lose 1 electron, and they're going to have a +1 charge, a cation. The alkaline earth metals, they are going to lose 2 electrons and are going to become have a 2+ charge. The halogens are going to gain 1 electron, becoming an anion, in order to be like the nearest noble gas. The oxygen family are going to try to gain 2 electrons. And the whole point of trying to be like the noble gases is because noble gases are very, very stable. So in ions are going to have a charge overall. They're either going to become cations or anions. In the main group, we can predict that. In the transition metals, we are not able to predict that. They are going to have different charges, various charges depending on their width. So the main group tends to lose electrons, forming cations with the same number of electrons as nearest noble gas. The main group nonmetals are going to tend to gain electrons in order to become like the nearest noble gas. So in general, this is more anion because these are gonna be the ones that like to gain electrons. More cation, they like to lose electrons. It's important to realize how do we write this losing or gaining electrons. When we are going to lose an electron, we are going to put the electrons on the product side. The ion charge is going to be the number of protons minus the number of electrons. For example, lithium has an atomic number of 3. And let's say lithium loses 2 electrons. So 3 minus 2, lithium is going to carry a charge of +1. And later on, right now, I will tell you how much you're losing or gaining. But later on, you're going to be able to determine this by yourself. On the other hand, you have fluorine. Fluorine likes to gain. Since it likes to gain, you're going to put it on the reactant side. And once again, the charge is going to be calculated by the number of protons minus the number of electrons. In here, it's saying that fluorine, every time you think of fluorine, you should be thinking of number 9 because the atomic number is number 9, which means it has 9 protons. In here, it's saying that it actually gained 1 electron. So instead of 9, you're going to have 10. Therefore, the charge is going to be 1. When there is no charge, so for example, if it's just like this, it means that it has 9 protons and 9 9 electrons, because that means that it is it doesn't have a charge. It's neutral. It doesn't carry a charge. The minute it carries a charge, that means it either lost or it gained electrons. This I highly encourage you to memorize. These are the charges that like to form. Lithium, sodium, potassium, those like to lose one electron, lose one electron. They like to lose two electrons, like to gain one, gain two. This one likes to gain three. These ones are interesting. They like to lose. So aluminum likes to lose three, gallium three, and so on. So it's important for you to memorize this. It's gonna be very helpful for you. So I'm gonna give you a practice for you to do on your own. So the answer for the first one, a nickel with 26 electrons. Well, how many protons? Nickel is Ni, so it'll be 28 minus 26. The answer should be +2, the cation. A bromine with 36 electrons. Well, what is the protons? How many protons? It's 35. 35 minus 36 equals -1, anion. Phosphorus. Phosphorus is number 15. 15 minus 18 equals -3. Determine the number of protons and electrons in aluminum 3+. Well, what is aluminum? The atomic number of aluminum is 13. 13. So that's how many protons, right? And then the ion here, so we're doing opposite. So protons, it's going to be 13. The charge is 3+. So basically we're solving for the electrons, which is going to be 10. Another question for you to practice. The answer will be atomic number. Okay, going back to the atomic mass. The atomic mass is the number that you're going to see below. Sometimes it's going to be called atomic weight or standard atomic weight. The atomic mass of each element is directly beneath the element, the symbol that you see. It represents the average mass of the isotope. So basically all the isotopes composed, that's what is going to be represented. Here, you're going to see an equation that is going to allow us to determine the average mass, the average atomic mass. And for that, we're going to need the abundance of each isotope. This means sum, the fraction, so you can put it in percentage decimal, makes it easier, times the mass. So for example, notice that in here, if we apply this formula, it would be 0.6915 times 62.9296 plus 0.3085 times 64,962.78. 64, what am I doing? 64,992.78. And that will give you the average atomic mass once you do the calculation. So if you have many different isotopes, you just keep taking them and take the sum of all of them. Here's an example. Natural chlorine, so they're giving you the abundance and they're giving you the mass. Abundance and mass. How can we calculate the atomic mass? So you want to remember the formula, right? So what you're going to do is you're going to take the abundance convert it to decimal. So pretty much I'm gonna, if you do the sum, it's going to be, and it's the same thing they have at the bottom, but I will just do 0.7577 times 34.97 plus 0.2423 times 36.97. And the answer should be 35.45 AMU. That's the unit for atomic mass. And if you look at a periodic table, you should see that that's what you're going to see. Here's another question for you to try on your own before I give you the answer. Here's your answer. Now, I want you to see this question, and you're gonna have some of the homework like this. You're gonna have something very similar on the exam. Now, notice that I'm asking you for the percent composition. I'm not asking you for the average mass. So take a minute and try to solve it yourself. The idea is that you solve it as an algebra problem. So they're giving you the average. So the average is 35.453 equals, you don't know the percentage, so let's call that X, times the mass is 34.96885, plus, you don't know the percentage of the second isotope, so we are going to call it Y, times 36.96590. Now this just became an algebra problem. You have two different integer here. We can't solve a problem with two unknowns. So what you do know that X plus Y equals 100 because the abundance are going to equals to 100. Let's make it simple. Since here we need a fraction, let's make this X plus Y equals 1. Okay? Now let's substitute the Y. So Y equals 1 minus X. So that means that wherever you see Y, you're going to substitute it. So you're going to have 35.4, oops. 35.453 equals X times 34.96885 plus, and then I'm gonna substitute that Y with 1 minus X, put it in parentheses, times 36.96590. And then from there, just solve for X. The only thing that I ask you is to make sure that you know that in this case, your X represents chlorine 35 and your Y represents chlorine 37, because you're gonna have to go back and tell me that. So when you manipulate this, you're pretty much are going to end up with 35.453. X times that is going to be 34.96885X plus 1 times 36 point, so that's going to be plus 36.96590 Be careful, this is negative. Negative x times this. So it's gonna be minus 36.96590x. Then collect like terms, and you're gonna see that your x equals 0.7576. Okay, so that's your x. What is your y? Go back and solve for your y. So your y is going to be equals 1 minus 0.7576, which comes out to 0.2424. This is the fraction. So if you want to multiply it by 100 to get 24.24%, this is going to be your y, which is chlorine 37. And this times 100, which is going to be 75.76%, which is going to be your chlorine 35. As long as you give me this on your exam, you will be fine. So I have one for practice for you guys, and here's the answer if you didn't understand my chicken scratch. It's very important that you know how to do this. This completes the second part, and then in a minute, we're gonna do the last part of the chapter. See you soon. Hello, we are going to continue with the next part of this chapter, and we're gonna start discussing molar mass. Molar mass is pretty much a way for us to count how many atoms there are by weighing them. The difference between molar mass and atomic mass is literally the units. What we're going to be using is, as you know, atoms are very small. So if we want to count, we're not going to say, can I have 1,000 atoms? You're not going to do that because they're too tiny. It's like if you go to the beach and you want to have 1,000 grain of sand. We don't do that. So we do a dozen. So what we want to do for us, a dozen means 1 mole. So when we're counting, instead of saying a dozen, we say 1 mole. That's for chemists, that's pretty much what we use. Now, a mole equals this number, 6.022 times 10 to the 23rd power. That is Avogadro's number. That unit for that number can be different depending on what you're referring to. For example, if you say 1 dozen apples or 1 dozen marbles, right? Or 1 dozen grain of sand. So for us, we're gonna say 1 mole of marbles, which that number equals 6.02 times 10 to the 23rd power, just like 1 dozen means 12. So we can say 1 dozen of marbles, which means 12 marbles, right? Or we can say 1 mole of marbles, which means 6.022 times 10 to the 23. Except we're not going to be referring to marbles or sand grains. We're actually going to be referring to atoms of a particular element, or molecules of a particular compound, or ions, or photons. So we're going to change that. The only thing is we're never going to use grams. We're not going to use that. So the mole is 6.022 times 10 to the 23. The mole is defined as the amount of a chemical substance that contain as many elementary entities. So that number can have a unit of atoms, molecules, ions, electrons, or photons. Okay? They are going to be, so when we do the molar mass, it's going to be grams over moles. So mass in grams means 1 mole of any substance has that many grams. So for example, if I tell you 1 mole carbon, how many grams? 12 grams, not 6.022 times 10 to the 23. Where did I get the 12 grams? That's the mass that you see underneath the number. 1 mole of hydrogen equals 1 gram. 1 mole of water equals 18 grams. Why? Because hydrogen is 1 gram. Since you have 2, 1 times 2 equals 2, plus oxygen is 16 grams. So 2 plus 16 equals 18. That's how you calculate the molar mass. 1 mole of zinc equals 65.4 grams. This we got from the periodic table. 1 mole of carbon, 12 grams. 1 mole of magnesium, 24.3. 1 mole of copper, and so on. So, which means that our mole to gram ratio is a conversion factor. So 1 mole of carbon equals 12 grams, or 12 grams of carbon equals 1 mole. And we can flip that as we need it. We can flip that. We can say that 6.022 times 10 to the 23rd atoms of carbon equals 12.01 grams. So notice that we can use this. And I know it may sound a little bit confusing, but with practice, you're going to realize the key is to understand that a conversion factor is a definition. So it is true that in 1 mole of carbon, you have 12 grams. It is true that in 6.0 times 10 to the 23 carbon atoms, you have that many grams. Okay, so when we are converting, we have to remember that if we are converting from grams of any elements to moles, you're going to use the molar mass. Okay, when you are going moles to atoms, you're going to use Avogadro's number. Do not use Avogadro's numbers here. Do not use Avogadro's number. Okay, so let's do an example. What is the mass? So that means they want their answer in grams, and they're giving you molecules. Okay, there is no direct relationship, so come out with a plan. You're going to go from grams to moles to molecules, okay? And then in here, you're going to have a conversion factor, right? So grams is gonna be at the bottom because you wanna cancel it. At the top, you're gonna have moles. Then here, you're gonna have moles at the bottom and molecules at the top. Where you're gonna get 1 mole of nitrogen dioxide. And the way we do that is 1 nitrogen and you have 2 oxygen. So 14 plus 2 times 16. This is the molar mass. So this number is going to be here, 46.01 grams in 1 mole. So we flip that. Then 1 mole equals 6.022 times 10 to the 23 molecules. Notice that this is what they did here. Your units cancel. The only unit that's not cancel is the desired unit that you want, which is gonna be in grams. And I actually did it wrong, sorry. They gave you molecules. They gave you molecules, they didn't give you grams. They gave you molecules, which means that at the bottom you have molecules. And at the top you have moles. And then moles to grams. So, sorry, I apologize. We made mistakes too. Let me erase this. Day 1, so your final answer should be grams, but they are giving you molecules. So the plan is to go from molecules. There is no direct relationship between molecules and grams. So you're gonna go to molecules, to moles, to grams. So molecules, they're giving you, so you wanna have molecules at the bottom. And here moles at the top. So you're gonna have 1 mole equals 6.022 times 10 to the 23. Then you wanna cancel 1 mole, and at the top, you're gonna have grams, which is the molar mass, 46.01. Moles and moles cancel, molecules cancel with the molecules that was given to you, and your answer should be 365. Notice that it has three significant figures because originally they gave you three significant figures. Here is another question where we are going from moles to atoms. And what am I giving you? I'm giving you an atom. I'm giving you helium. So what, there is a direct relationship. So you have either use this or 1 mole of helium, 6.022 times 10 to the 23. Which one do you want to use? Well, you're going to start with what's given to you, 3.5 moles. You want moles at the bottom, so you're going to use the first one. And there you go. Notice that your moles and moles cancel, top and bottom cancel, and the only unit does not cancel is your desired unit. Here's another example. I encourage you to watch the videos I have posted for extra understanding. And here we going from atoms to moles. So it's the opposite of what we did on the first problem. So in this case, you are going to use, since you've got atoms, atoms must be at the bottom. Notice that your atoms and atoms cancel, and you will have your desired unit. This other problem is actually giving you grams, and they want to know moles. So you're going to need the molar mass. The molar mass is 1 mole of carbon equals 12.0 grams of carbon. Notice that you start with what it's giving you. You put grams at the bottom, and your final answer should be in moles. We're going to do some practice problems, so don't worry. This one is a little bit more tricky. They're giving you, they want atoms, but they're giving you grams. So your plan is to go from grams. There's no relationship, direct relationship. So you're gonna go from grams to moles, moles to atoms. And here you go. You have grams, moles, cancel moles, to atoms. Try this on your own. Notice that they're giving you grams and they want to know atoms. So you want to start with grams to moles to atoms. 65.55, which is what's given. And then you want grams at the bottom and moles at the top. So in order to go from grams to moles or moles to gram, you always need the molar mass. The molar mass is 63.55 grams in 1 mole. Notice that your grams cancel. Now you want to get rid of moles. How do you get rid of from moles to atoms? Avogadro's number. 0.22 times 10 to the 23, 1 mole. Your units cancel. Your answer is going to be 6.0. 22 times 10 to the 23 power. Now, I really, really enjoyed this question. It's asking you for how many atoms, okay? How many atoms? Be careful because in here, I'm gonna give you a clue. You're going to go from grams to moles to molecules to atom. Why? Because I gave you a molecule. Okay, how many? I gave you 1 molecule, which has 3 atoms. So figure that out. I really encourage you to do this on your own because you're going to have something similar on the exam. Here's the answer. This is the beginning of lots of calculations we're going to be doing. So if you are a little bit um, confused, please make sure you ask questions, plenty of questions, before things get a little bit more complicated. Okay, I have placed some videos at the end so you guys can watch them. And there's also lots of practice questions with the answer so you can try on your own. This concludes the second chapter, or general chemistry.